12,900 years ago, there was a terrible catastrophe in North America. All large animals weighing more than 100 pounds, the so-called megafauna, became extinct. This included mastodons, camels, American lions, and saber-toothed tigers. Humans were not spared. The Paleolithic Clovis culture also disappeared. The extinction coincided with a glacial period called the Younger Dryas cooling event. Its onset was sudden, and it lasted for approximately 1,300 years. A cosmic impact smaller than the one that killed the dinosaurs could have caused the extinction and the cooling event, but the biggest problem with this hypothesis is that the impact crater for such a colossal impact has not been found. In this presentation, I will review some of the evidence that has been proposed to establish that an extraterrestrial impact did in fact occur, and I will also mention the objections raised by scientists who oppose the impact hypothesis. I will conclude by describing how the mathematical study of the Carolina Bays can help to find the location of the extraterrestrial impact and estimate the energy of the cosmic collision. In 2007, Firestone and 25 co-authors proposed that an extraterrestrial impact caused the extinction of the North American megafauna and triggered the Younger Dryas cooling event. This paper reported microspherules and nanodiamonds at the Younger Dryas boundary as evidence of an extraterrestrial explosion over North America that destabilized the Laurentide ice sheet and caused extensive biomass burning. Samples were taken from 15 Carolina bays because previous authors had proposed that the bays had originated from an extraterrestrial impact. Since no crater had been found, Firestone proposed that one or more large, low-density extraterrestrial objects exploded over northern North America. Based on hypervelocity impact research by Professor Peter Schultz, he also suggested that multiple large meteorites hitting the 2-kilometer thick Laurentide ice sheet at angles less than 30 degrees would have left negligible traces after the glaciers melted. In 2009, Firestone replied to criticism about the 2007 paper. Firestone maintained that the spherules at the Younger Dryas boundary were suitable indicators of an extraterrestrial airburst, and that the conflicting dates for the Carolina Bays could have resulted from inadvertent sampling of older sediment that may have shifted over time. He also renewed his assertion that an impact on the Laurentide ice sheet could have shielded the ground and prevented the formation of a crater, as had been demonstrated by Professor Schultz. Firestone pointed out that the radial alignment of the Carolina Bays and the Nebraska rainwater basins was an indication of an extraterrestrial explosion in the Great Lakes or Hudson Bay, as shown in this image. He attributed the formation of the elliptical depressions to the wind from the shockwave, which he said was consistent with the theory that the bays were aeolian in origin, as proposed by previous researchers. Firestone's 2009 paper brought attention to the Nebraska rainwater basins that had been discovered in 2001. By 2010, the wide availability of LiDAR data allowed Michael Davies to integrate hundreds of LiDAR images with Google Earth. He used great circle trajectories adjusted for the Coriolis effect to calculate the convergence point of the bays at Saginaw Bay. Previous attempts by others to find the focal point had failed because they had used straight lines on flat maps and they had ignored the flight time of the projectiles. The discovery of the Nebraska rainwater basins was crucial for the triangulation effort because previous impact researchers had thought that projectiles of extraterrestrial origin had formed the Carolina Bays. In addition to calculating the convergence point, Michael Davies established a publicly available LiDAR database that is a great resource for research on the Carolina Bays. In 2011, Nicholas Peintner and 6 other university professors from the US, the UK, and Austria collaborated on a Requiem paper declaring the death of the Younger Dryas impact hypothesis. In the Roman Catholic Church, a Requiem is a mass for the repose of the souls of the dead. The paper went point by point over Firestone's claims and showed that none of his evidence could be conclusively considered indicative of an extraterrestrial impact. Firestone's papers had not shown an impact crater, meteorite fragments, petrographic shock metamorphism, enrichment of siderophile elements, or other criteria established by impact science. The microspherules reported by Firestone had not been established by any previous research as a specific characteristic of extraterrestrial impacts. The Requiem paper referenced a 2007 publication by Ivester that described an episodic formation process for the Carolina Bays. The Requiem paper was very influential in stopping funding and research on the Carolina Bays. In 2012, Mark Boslow, a physicist, and 15 co-authors published their objections to a Younger Dryas impact event and its hypothesis. They noted that several versions of the Younger Dryas impact hypothesis had been published and that the fragmentation and explosion mechanisms proposed for some of the versions did not conserve energy or momentum, that physics-based models had not been presented to support the various concepts, and that the chance of a large comet impacting the Earth during the time period specified was infinitesimal. In addition, the authors listed three major objections. First, there is a lack of impact evidence because no impact craters of the appropriate size and age are known, and no shock material or other features diagnostic of impacts have been found in Younger Dryas sediments. Second, the climate and archaeological features attributed to a Younger Dryas event can be explained by mechanisms that do not require an impact. And third, the authors believed that the Younger Dryas proponents misrepresented some of the evidence used to argue for an impact, and several independent researchers were unable to reproduce reported results. The lack of impact evidence is a justifiable criticism, but misrepresentation of evidence is a grave accusation against the honesty of the scientists, and this has created great hostility between proponents and opponents of the Younger Dryas impact hypothesis. The proponents of an extraterrestrial impact at the Younger Dryas boundary are very persistent and not easily discouraged by criticism. In 2012, several papers evaluated the microspherules evidence, and additional microspherules were found in Mexico. In 2013, James Whitkey and 27 other collaborators quantified the amount of microspherules across 4 continents attributed to an extraterrestrial impact. This was one of the largest investigations undertaken regarding spherules geochemistry and the processes of spherules formation. The spherules from 18 sites across North America, Europe, and the Middle East were investigated with X-ray spectroscopy and scanning electron microscopy. The research also produced spherules from wood in the laboratory at more than 1,730 degrees Celsius, indicating that impact-related incineration of biomass may have contributed to spherule production. The authors estimated that 10 million tons of spherules from a cosmic impact were distributed across 50 million square kilometers. Before the ink was dry on Whitkey's paper, Boslow and 3 co-authors sent a letter to the Proceedings of the National Academy of Science repeating the criticism that the impact hypothesis did not have a physics-based model and that the arguments presented in the paper demonstrated a misunderstanding of comets as well as the physics of airbursts. Whitkey's paper was criticized for the description of how comets break apart by gravitational forces, and also for stating that the thermal radiation of the comet passage was enough to melt iron-rich and silicon-rich surface sediments at more than 2,200 degrees Celsius. Boslow clarified that such temperatures are only exceeded in the air shock during brief hypervelocity transit over a small area near the front of the bow shock before a complete ablation or dark flight. Of course, Boslow is right about the physics. He has conducted many computer simulations of impacts and he has extensive experience with meteorites. An obvious question is, why don't these guys get together and work on a model that is acceptable to all, instead of just throwing barbs at each other? In 2013, Petayev and his Harvard University co-authors found a large platinum anomaly in the Greenland ice sheet that added support to an extraterrestrial event at the Younger Dryas boundary approximately 12,900 years ago. Platinum is a siderophile element that could have originated from an extraterrestrial impact. The platinum anomaly at the Younger Dryas boundary occurs in many places in North America, according to a publication by Christopher Moore in 2017. The layer with platinum is consistent with the Greenland ice sheet data that indicated atmospheric input of platinum-rich dust. This platinum anomaly may serve as a widely distributed time marker for correlation with the onset of the Younger Dryas cooling event. Unlike the microspherules that continue to be contested as evidence of an extraterrestrial impact, the platinum anomaly reported by Petayev looks like solid evidence that there was an extraterrestrial impact at the Younger Dryas boundary. Petaev proposed that the projectile was an iron meteorite that was unlikely to result in an airburst, which means that it must have impacted the Earth's surface. Even though Firestone called attention to the radial alignment of the Carolina Bays and the Nebraska Rainwater Basins in his 2009 paper, subsequent research on the Younger Dryas impact hypothesis tried to avoid association with the impact origin of the bays because there was a perception in some scientific communities that the research was unprofessional due to the early naive bay genesis claims. The great diversity of dates obtained from the subsurface of the bays was interpreted to mean that the bays were created over thousands of years, rather than from a single event. Since the dates were obtained by very precise methods, trying to correlate bay genesis with an impact event seemed like an insurmountable task. The most powerful arguments in favor of the impact origin of the Carolina Bays are their radial alignment and their elliptical geometry, which cannot be achieved by wind and water mechanisms. Many researchers have described the Carolina Bays as either oval or elliptical. Melton and Shriver in 1933 and Prouty in 1952 characterized the bays as elliptical, but they did not perform the geometrical analysis to verify that the bays were mathematical ellipses. Using LiDAR images, it can be shown that an ellipse with the same width-to-length ratio as the Carolina Bay fits the bay exactly after scaling and rotating the ellipse. This makes it possible to conclude that the archetype shape of the Carolina Bays is elliptical and that the bays can be modeled as mathematical conic sections. Many bays have been deformed by terrestrial processes and human activity, but the bays that are well preserved have an elliptical shape. The Carolina Bays and the Nebraska Rainwater Basins have similar ellipticity, even though they have different axial orientations and they are separated by 2,000 kilometers. The elliptical shapes correspond to cones inclined at about 35 degrees. The predominant elliptical geometry, with width-to-length ratios of 0.58 plus or minus 0.05, is the most convincing evidence that the bays were not formed by ordinary terrestrial processes. The Carolina Bays and the Nebraska Rainwater Basins are found on unconsolidated soil close to the water table. The bays in Nebraska are on terrain that is 600 to 700 meters above sea level on ground that has not been close to any sea for 60 million years. The occurrence of elliptical features with identical geometry in Nebraska and in the East Coast, oriented toward the Convergence point in Michigan, requires a better explanation than just Aeolian and lacustrine mechanisms that cannot guarantee the shape or orientation of the resulting structures. The Glacier ice impact hypothesis, published in 2017, proposed that the Carolina Bays and the Nebraska Rainwater Basins were made by secondary impacts of glacier ice ejected by a meteorite impact on the Laurentide ice sheet approximately 12,900 years ago. The impacts of the ejected ice chunks with energies of 13 kilotons to 3 megatons produced seismic vibrations that liquefied on consolidated ground, and the ice projectiles created conical cavities inclined at about 35 degrees that were remodeled into shallow elliptical bays by viscous relaxation. The extraterrestrial impact and the saturation bombardment by the glacier ice boulders caused an extinction event within a radius of 1,500 kilometers from the impact point. Water ejected above the atmosphere produced a fog of ice crystals in low Earth orbit that blocked the light of the sun and triggered the global winter. Although the creation of the Carolina Bays could have occurred at any time during the Ice Age, the date of the extraterrestrial impact is deduced from the disappearance of the North American megafauna and the onset of the Younger Dryas cooling event. The glacier ice impact hypothesis used an experimental physical model to demonstrate the creation of conical impact cavities and viscous relaxation. The model made it possible to determine the origin of the raised rims around the Carolina Bays, the mechanism for the formation of overlapping bays, the stratigraphic restoration of the subsurface, and the deformation of bays on inclined terrain. The creation of the bays by plastic deformation on liquefied ground, followed by stratigraphic restoration through viscous relaxation, explains why the dates of the subsurface of the Carolina Bays correspond to the date of the terrain, but not to the date of bay formation. This makes it possible to ignore the diverse dates of the terrain and associate the emplacement of the bays with the extinction event. Every time a new publication comes out in support of the Younger Dryas impact, many critics rush to contradict the evidence in a perverse game of whack-a-mole. Of course, it is necessary for the science to be right, but the objections by themselves do not advance our knowledge of what happened 12,900 years ago. It is almost as if the critics just want another bibliographic citation and don't really care about correcting the myths that the megafauna were exterminated by Paleolithic people or climate change, and that the bays in Nebraska and the East Coast were made by wind and water. Correlating ellipses with cones, which was something known to the ancient Greeks, and making a conjecture that the radial orientation of the bays may provide information about the location of an extraterrestrial impact may not seem controversial, but there are critics who think that even if the bays were actually caused by an impact, Google Earth depictions of the Carolina bays are unacceptable as evidence to prove that such an event occurred. This is absurd. New imaging technologies like Google Earth and LiDAR expand the frontiers of science. The telescope opened the heavens to Galileo, and LiDAR has given us a clearer view of the Earth's surface. With the telescope, Galileo found that the surface of the moon was covered with craters, and LiDAR has enabled us to see that many Carolina bays are perfect ellipses, which can be treated mathematically as conic sections. The glacier ice impact hypothesis uses the laws of physics as the mathematical foundation for calculating the characteristics of the Carolina bays and the extraterrestrial impact. The conic sections representing the Carolina bays and the convergence point in Saginaw Bay provide the initial conditions for the physics-based model. The bay geometry provides launch and impact angles. Ballistic equations using the distance between the convergence point and the bay provide the speed, height, and flight time of the trajectories. Yield equations correlating energy with crater size provide the mass and volume of the glacier ice projectiles. The energy of the extraterrestrial impact can be estimated by combining the information from all the bays using the laws of energy conservation. The speeds required to launch ice projectiles from Michigan to the East Coast vary from 3 to 4 kilometers per second at angles of 35 to 45 degrees. All the ballistic trajectories are suborbital space flights with heights of 150 to 370 kilometers and flight times of 6 to 9 minutes. Since the atmosphere extends only to about 100 kilometers, a substantial portion of the trajectories is in the vacuum of space. Above 35 kilometers from the Earth's surface, the atmospheric pressure is below the triple point of water, and water cannot exist as a liquid. Any liquid water ejected above the atmosphere would have produced clouds of ice crystals that block the light of the sun. Knowing the speed of the ice boulders, we can use scaling laws relating energy to crater size for estimating the mass of the projectiles. The scaling laws were derived from detonations of chemical explosives and nuclear bombs in the 20th century. The University of Arizona had a program that implemented the scaling equations from the book by Professor J. Melosh. This program calculated that a Carolina bay with a diameter of 1 kilometer could have been created by an impact of an ice sphere with a diameter of 180 meters traveling at 3 kilometers per second with an energy of 3 megatons. This ice boulder would be about the size of Yankee Stadium in New York. Professor Melosh's extensive treatise about impact cratering also considers atmospheric effects on projectiles entering the atmosphere. Atmospheric drag and gravity in the presence of ablation interact to slow down a constantly shrinking projectile and make its angle of impact more perpendicular to the surface. The change in speed is inversely proportional to the mass of the projectile, so a small projectile has a more vertical impact than a larger projectile with a similar initial trajectory. Professor Melosh's equations provide the physics-based model for Melton and Shriver's original observations in 1933 about bay ellipticity. Prouty added additional data points in 1952 to produce this figure of ellipticity versus bay size. The trend is very clear. The smaller bays are rounder and less elongated than larger bays. Rounder bays correspond to a more vertical angle of impact in accordance with the equations. The size and the energy of the ejected ice boulders can be used to estimate the characteristics of the extraterrestrial impact. Ideally, the ballistic trajectory associated with each Carolina Bay should be used to calculate the speed of the ice projectile, which can then be used with equations relating energy to crater size to calculate the energy that formed each bay. The law of conservation of energy allows us to add the energies of all the bays to estimate the energy of the extraterrestrial collision, although the actual energy of the impact would have been greater because some energy was used to melt ice and convert water into steam. Since there are at least 500,000 Carolina bays, the combined energy corresponds to an impact by an asteroid with a diameter of 3 kilometers. From the combined volumes of the glacier ice projectiles, we can also calculate that 1.5 trillion cubic meters of ice ejected by the extraterrestrial impact would cover half of the United States to a depth of half a meter. If the ice sheet had a thickness of 1 kilometer at the point of the extraterrestrial impact, the circular area containing this volume of ice would have had a diameter of 44 kilometers. These calculations underestimate the energy of the extraterrestrial impact because we did not take into account the ice boulders that fell on hard ground and did not form bays. For an extraterrestrial impact on ice, a physics-based model needs to take into consideration the thermodynamics of water. This chart illustrates the energy required to convert ice into water and water into steam. 80 calories are required to convert 1 gram of ice at 0 degrees Celsius into 1 gram of water at 0 degrees Celsius. All the 80 calories just change the phase of the water without changing the temperature. This is called the heat of fusion. For liquid water, the temperature increases by 1 degree Celsius for each calorie added per gram until the boiling point of 100 degrees is reached. 1 gram of water at 100 degrees requires 539 calories to turn into 1 gram of steam at 100 degrees. This is called the heat of vaporization. Above 35 kilometers from the Earth's surface, atmospheric pressure is below the triple point of water, and water can only exist as solid ice or water vapor as illustrated in this phase diagram. As the pressure decreases, water evaporates by extracting heat from the adjacent water until the remaining water freezes. The calories required for phase transformations can be used to calculate how much water is converted into ice crystals. For water at 100 degrees Celsius in a vacuum, 25% evaporates and 75% turns into ice crystals. For water at 0 degrees Celsius, 13% evaporates and 87% turns into ice crystals. In an impact scenario, these ice crystals would go into low Earth orbit and block the light of the sun. The ice crystals would eventually sublimate into water vapor, ending the global cooling event. Sublimation is the direct conversion of ice into vapor, which requires the energy of the heat of fusion plus the heat of vaporization, which is 619 calories per gram. From the duration of the Younger Dryas and the rate of sublimation, it is possible to get a rough estimate of the amount of water ejected by the extraterrestrial impact on the Laurentide ice sheet. The elliptical geomorphology of the Carolina Bays and the Nebraska rainwater basins provides the basis for a physics-based model of an extraterrestrial impact because the conic sections are the result of the fundamental forces that created the bays. The glacier ice impact hypothesis provides a plausible mechanism for the formation of the bays and explains their morphological features and the diverse dates of the terrain on which the bays are found. It is time to resume research on the Carolina Bays and consider their geometry and their transformations by terrestrial processes after their emplacement. The study of the Carolina Bays promises to give us a clearer picture of the cosmic event that devastated North America 12,900 years ago.